if it's not deforming to the sides, that means that it's not going to develop any stress to the sides. So your horizontal stress is going to be 0. If Poisson ratio is 0, it doesn't develop stress to the sides as it gets buried next to some other rock. What about if the Poisson ratio is 0.5? This is going to be 1, which means that now that if this is the solid and you push in this direction, it's going to deform quite a bit into, well, it's not going to, let me do this again. I messed it up here. Actually, in this case, it's not going to deform at all. And because it's not going to deform, and it's not going to change volume with that condition, all the stress that you put in this direction is going to be applied on the other directions too. This is like a fluid, right? It's like a fluid that pushes with all its weight also to the sides. But these two extremes are not really good representations of an actual rock. What is the typical Poisson ratio of an actual rock? Do you know more or less? 0.3. Yeah, 0.3. It's a little bit high, probably 0.3. But let's try to explore this here in the middle. 0.25. What is going to be the value of this guy for 0.25? No. 0.333, right? So 1/3. And 1/3 is going to be over here, and that's going to be a point over here. And then, you know, if I join this with the line, it's going to look something like this. And this is going to be an important number also to remember. The number 3, or 1/3. Okay, we're going to see that a lot later on. But it's going to be 1/3. And in this case, if you push here with a given strain, with a given stress, it is going to expand to the sides, and it is going to create a stress which is not as large as the one you're pushing on the top, but it's not 0 either. It's 1/3. So you push in this direction with 1,000 psi. Well, in the sides you're going to have 333 psi in both directions, this one and that one. And in order to complete this picture, typically the Poisson ratio of rocks goes from about 0.1 to about 0.3, as Ms. Montero said. But there are some other kind of rocks also that get closer to 0.5 and to higher Poisson ratio. Probably here you will find something that we're going to learn what is this word later on. But mud rocks are going to have an effective Poisson ratio which is tends to be high. Salt rock also is going to deform and push to the sides with the same stress, overburden stress, and that's going to allow them to have a very large horizontal stress compared to typical rocks. And here in 0.5 we're going to have the fluids. And this is something we already knew, right? So if we're here, the horizontal stress is going to be the same as the vertical stress, which is what we know is the condition of pressure, which is the same in all directions. Okay, so we have 3 more minutes, and I'd like And I'd like to give you the equations that you need in order to solve the homework. Let's start to that equation, okay? Now I'm going to say that, remember that before we said that these two were 0? Where now I'm going to say that epsilon 1,2 is different than 0, epsilon 2,2 is different than 0, and epsilon 3,3 is different than 0. I'm going to, same as I did before, assume that those are the horizontal and this is the vertical. And I'm going to further say that epsilon 1,2, epsilon 1,3, and epsilon 2,3, those are equal to 0. It's no shear strain. As a result, we're not going to go through the derivation because it is just math. But as a result, you're going to see that sigma 1,1 and sigma 2,2, now the full equations are going to look something like this. So let me just come back here. But it's the same thing. I apply that matrix I was showing. There's going to be no proportionality coefficient here. And this one looks very similar, and it's like that. All right, so what happened now? Now our stresses, look, this guy is the same as before. This is horizontal stress due to overburden. The same thing than the one we saw before, right? But now we have two additional terms. Those two additional terms are the ones called tectonic stress. And because those are called tectonic stress, the epsilon 1,1 and the epsilon 2,2 are called tectonic stress. Right here, right? Thank you. So you may ask now, so what is the value of those tectonic stress? We don't know. That's something we have to determine. And that's usually calibrated from field data. But in that way, now we can calculate the stresses, horizontal stresses, that are actually higher than the vertical stress, or higher than what you expect just because of overburden. So now that everyone is here, let me tell again that I'm going to confirm with the email if there is lecture on Tuesday or not, because I'm planning to go to ATC. Okay? Somebody had a question? You, Michael? No? Mr. Lawe?
Still linear elasticity?
Yes. Still all is linear elasticity.